The cosmos follows a set of rules, but it secretly breaks them right in front of us. We have built our entire understanding of reality on laws of physics that seem absolute, like gravity and relativity. Yet the universe has a habit of tearing pages from its own rulebook without any warning, leaving even the most brilliant scientists utterly baffled. What if everything we think we know is just the surface of a much deeper and stranger truth? We are about to embark on a journey through 22 of the most shocking ways the universe contradicts itself. You will discover cosmic puzzles where particles communicate instantly across infinite distances, where empty space pushes galaxies apart, and where black holes threaten to erase information from existence. By the end, you will see the fundamental laws of nature in a completely new and unsettling light. How can time simply disappear from the equations of quantum gravity? And why does the ancient light from the Big Bang seem to point in a single preferred direction? These are not small gaps in knowledge. They are chasms that suggest our reality might be a projection from a lower dimensional boundary. What does it mean for our place in the cosmos if the rules themselves are not fixed? For over a century, the twin pillars of modern physics have stood firm. Einstein's theory of relativity masterfully describes the grand cosmic dance of planets, stars, and galaxies, a world where gravity is the curvature of space-time itself. At the other extreme, quantum mechanics reveals the bizarre and probabilistic rules governing the subatomic realm, a world of ghostly particles and spooky connections. These frameworks are the most successful scientific theories ever devised, predicting everything from the existence of black holes to the behavior of semiconductors in your phone. We trust them because they work with a precision that borders on the miraculous, yet the very architects of these theories sensed their incompleteness. Einstein himself was deeply troubled by the implications of quantum mechanics, famously stating that God does not play dice with the universe. Stephen Hawking spent his career grappling with the fundamental contradictions that arise when these two powerful sets of rules are forced to meet. The first major crack in this seemingly solid foundation appeared not with a bang but with a whisper in the quiet observations of a Swiss astronomer named Fritz Zwicky. While studying the Coma galaxy cluster in the 1930s, Zwicky noticed something impossible. The galaxies were moving so fast that the visible matter within the cluster, all the stars and gas, could not possibly provide enough gravity to hold them together. According to the trusted laws of gravity, the cluster should have flown apart eons ago. The only explanation was that there was something else there, a vast amount of invisible mass providing the extra gravitational glue. He called this mysterious substance Dunkel Materie, or dark matter. This was not a minor adjustment. It was the first undeniable clue that our inventory of the cosmos was missing almost everything. The rules of physics were correct, but they were pointing to a reality far stranger than we had ever imagined, a universe dominated by forces and substances we cannot see. This initial discovery opened the door to a cascade of even deeper mysteries, where the laws of physics do not just hint at hidden ingredients, but appear to break down completely. Zwicky's dark matter was a ghost in the machine, a silent partner holding the cosmos together, but the next violation strikes at the very heart of cause and effect. Picture two particles born from the same event, twins sharing a single quantum identity. Now fling them to opposite ends of the universe. According to every rule we hold dear, they should become independent, their fates separate. Yet when you measure one, its distant twin instantly knows, mirroring its state in a perfect, synchronized dance. This is quantum entanglement, and Einstein famously dismissed it as spooky action at a distance, a phrase that perfectly captures its unsettling nature. He believed this strange connection was impossible because it seemed to violate a foundational rule of his own theory of relativity, the cosmic speed limit that says nothing, not even information, can travel faster than light. For decades, it was a philosophical debate, a paradox he formulated with his colleagues Podolsky and Rosen. But then, a physicist named John Bell devised a way to test it. His theorem provided a mathematical recipe to distinguish between a universe with hidden, classical variables and one that was genuinely spooky. When experiments were finally conducted, the results were unequivocal. The entangled particles were communicating, or at least coordinating, in a way that defied any local explanation. It is as if you had two magical coins. You flip one in New York and it lands on heads. At that exact instant, its paired coin in Tokyo, without any signal passing between them, also lands on heads every single time. This is not just an oddity, it is a fundamental rupture in our understanding of reality. How can one particle instantly influence another across a billion light years? What does this mean for the fabric of space and time if locality, the idea that objects are only influenced by their immediate surroundings, is simply an illusion? This spooky connection forces us to question whether the universe is truly made of separate, distinct things, or if at its deepest level, it is a single, interconnected whole where distance is meaningless. And if entanglement shatters our idea of space, then the next puzzle threatens to erase time itself from the equation. If entanglement shatters locality, then dark energy shatters our expectations for the cosmos on the grandest scale. For most of the 20th century, scientists believed the universe was expanding, a consequence of the Big Bang, but that this expansion was gradually slowing down. The collective gravitational pull of all the matter in the cosmos, from stars to dark matter, was thought to be acting like a cosmic brake, gradually reining in the outward rush of galaxies. It was a logical and elegant idea, a universe governed by a gentle deceleration. Then, in the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter, made a measurement that turned this entire picture on its head. They were observing distant supernova, using these exploding stars as cosmic mile markers to gauge the expansion rate of the universe across billions of years. To their astonishment, they found that the universe is not slowing down at all. Instead, its expansion is accelerating. Galaxies are flying apart from each other faster and faster as time goes on. It was as if you threw a ball into the air, expecting it to fall back to Earth, but instead watched it shoot upward into the sky with ever-increasing speed. This discovery was so revolutionary and so counterintuitive that it earned Perlmutter and his colleagues the Nobel Prize in Physics. The only conceivable explanation was the existence of a mysterious, repulsive force permeating the vacuum of space itself, a force we now call dark energy. This is a fundamental rule break. Gravity, the force that sculpts galaxies and holds planets in their orbits, should be pulling the universe together. Yet dark energy is doing the exact opposite, pushing it apart with overwhelming strength. Think of it as a cosmic tug of war where one side is not just winning, but growing inexplicably stronger with time. The implications for the ultimate fate of the universe are staggering. If this acceleration continues unchecked, we could be heading toward a scenario known as the Big Rip. In this bleak future, the repulsive force of dark energy would become so powerful that it would overwhelm the forces holding galaxies, stars, and even atoms themselves together. First, galactic clusters would be torn asunder. Then, individual galaxies would be ripped apart. Eventually, stars would be separated from their planets. And finally, atoms would be shredded into their fundamental components. The fabric of spacetime itself would be torn apart in a final, violent end. Dark energy is not just another component of the universe. It is a dominant and baffling phenomenon that breaks the most basic rule we had about cosmic evolution. It forces us to ask what empty space truly is, if it can contain such a potent anti-gravitational force, and if the vast emptiness of space can hold such power, what other rules might be written in the shadows waiting to be broken? This accelerating expansion driven by dark energy sets the stage for an even deeper conflict, one that unfolds at the very edge of space and time, within the ultimate cosmic traps known as black holes. Here, the two great pillars of physics, general relativity and quantum mechanics, are pitted against each other in a battle with seemingly no winner. General relativity, Einstein's masterpiece, describes a black hole as a perfectly smooth, simple object defined only by its mass, spin, and charge. It paints a picture of an event horizon, a point of no return from which nothing, not even light, can escape. If you were to fall in, according to relativity, you would cross this boundary smoothly, unaware of your impending doom at the singularity deep within. This elegant picture, however, contains a catastrophic problem for quantum mechanics. One of the most sacred rules of the quantum world is that information can never be truly destroyed. It can be scrambled, transformed, or hidden, but it must, in principle, be recoverable. Think of it like burning a book. The paper and ink are turned to ash and smoke, a chaotic mess. But in a quantum universe, if you could somehow collect every single particle of ash and wisp of smoke, and account for the precise energy and light released, you could theoretically reconstruct the book perfectly, down to the last comma. The information was never lost, only profoundly rearranged. Now enter Stephen Hawking. In the 1970s, he made a stunning discovery. Black holes are not completely black. Due to weird quantum effects happening right at the event horizon, they slowly leak radiation, now known as Hawking radiation. This radiation carries away energy, causing the black hole to gradually shrink and eventually evaporate completely, vanishing from the universe. And here lies the paradox. Hawking radiation is random and featureless, like a steady hiss of static. It contains no information about the specific things that fell into the black hole. So when the black hole evaporates, what happens to all that information? The book, the astronaut, the entire history of everything that ever crossed the event horizon seems to be erased from existence forever. This is the black hole information paradox. It forces us to choose between two cherished theories. If Hawking is right and information is lost, then quantum mechanics is fundamentally wrong. But if quantum mechanics is right and information must be preserved, then our understanding of black holes from general relativity must be incomplete. To save quantum mechanics, physicists have proposed a radical and violent solution, the Firewall Paradox. Perhaps the event horizon is not a smooth gateway after all. Maybe it is a blazing wall of high-energy particles, a firewall that would incinerate anything attempting to cross it. This would prevent information from falling in the first place, but it directly contradicts the smooth spacetime geometry predicted by Einstein's equations. So we are left with an impossible choice: either accept that information is destroyed, breaking quantum law, or accept that the event horizon is a searing inferno, breaking relativity. This is not a minor technicality. It is a direct challenge to the logical consistency of our physical reality. How can the universe operate with two sets of rules that are fundamentally incompatible at the most extreme points? The resolution, if one exists, may require us to rewrite the rules entirely, suggesting that our most basic concepts of space, time, and information are mere approximations of a much deeper truth. While black holes present a theoretical crisis, a more tangible mystery was unfolding in our own cosmic backyard with two silent robotic explorers. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were humanity's first emissaries to the outer solar system. After completing their primary missions, they continued on a silent journey into the abyss, their faint signals tracked by NASA for decades. Yet, as they traveled farther from the Sun, a strange and persistent anomaly emerged. The probes were slowing down, not by much, just a tiny, almost imperceptible amount, equivalent to a 10 billionth of the gravity you feel on Earth. But according to our most trusted laws of motion, the laws of Newton and Einstein, this should not have been happening. Every known force had been meticulously accounted for, from the gravitational pull of the Sun and planets to the slight pressure of the solar wind. The deceleration was a mystery, a faint whisper from the void that the universe was not playing by the rules we had written for it. For years, this Pioneer anomaly baffled scientists. Was it evidence of a new force, a subtle tug from some unseen source like a halo of dark matter surrounding our solar system? Could it be a flaw in our understanding of gravity itself, a hint that Einstein's theory of relativity needed a slight modification over vast distances? Or was it something far more mundane, a simple engineering effect that had been overlooked? NASA scientists formed dedicated teams, spending years poring over decades of data, considering every possibility from the revolutionary to the routine. One researcher described it as a detective story with the entire cosmos as a crime scene. The most tantalizing explanation pointed toward the spacecraft themselves. The probes were powered by radioactive generators which produced heat. Perhaps this heat was radiating off the craft unevenly, acting like a tiny, unintended thruster, gently pushing the Pioneers backward. After an exhaustive investigation, this thermal recoil force was indeed confirmed as the most likely culprit. It was a subtle engineering detail, not a revolution in physics. Yet the story of the Pioneer anomaly is profoundly important. It reveals a deep truth about our relationship with the cosmos. For years, the data pointed to a fundamental rule break, a crack in the foundation of physics. It forced brilliant minds to question everything, to consider the existence of entirely new forces. This demonstrates that even our most well-tested laws operate within a certain comfort zone. When we push into new frontiers, like the deep space between stars, we might encounter phenomena for which our rulebook is incomplete. The universe is not just breaking its own rules, it is challenging us to discover where our understanding ends and true mystery begins. If a simple thing like heat radiation from a spacecraft can mimic the signature of new physics, what other subtle whispers are we misinterpreting as we listen to the cosmos? This lesson in humility prepares us for an even stranger deviation, one that does not involve distant probes or black holes, but the very constants that shape reality itself. The rules of thermodynamics seemed absolute, yet the universe's very first moments appear to have ignored one of them completely. Entropy, the measure of disorder, always increases. A hot cup of coffee cools down, it never spontaneously heats up. The universe should have begun in a state of maximum order, a smooth, dense, and incredibly hot soup. But when we look at the cosmic microwave background, the afterglow of the Big Bang, we see a sky that is almost perfectly uniform, with only tiny, random fluctuations. A universe starting in such a smooth, low-entropy state is like finding a library where every book is perfectly alphabetized and shelved by chance alone. It breaks the most fundamental rule of statistical probability. To resolve this, physicist Alan Guth proposed a radical idea: cosmic inflation. He suggested that a fraction of a second after the beginning, the universe underwent a breathtaking exponential expansion. Space itself stretched faster than the speed of light, smoothing out any initial wrinkles and creating the vast, flat, and uniform cosmos we see today. Think of it as a balloon being inflated to the size of the Earth in less time than it takes to blink. This incredible growth spurt explains the uniformity, but it creates a profound puzzle of its own: the graceful exit problem. What started this hyper-expansion, and more importantly, what made it stop? The mechanism that drove inflation, a hypothetical field called the inflaton, must have somehow decayed, converting its immense energy into the hot plasma of the Big Bang. But we have no idea why or how this transition happened so perfectly. As Guth himself noted, while inflation is a compelling framework, the details of how it started and ended remain deeply mysterious. This period represents a fundamental rule break, a moment when the universe operated under a completely different set of physical laws, where space expanded in a way that seems to violate causality and redefine what is possible. If the cosmos can rewrite its own operating manual for a fleeting instant at the beginning of time, what other hidden clauses might be buried in its foundation, waiting to be triggered again? Gravity feels like the most powerful force in our daily lives, holding entire galaxies together and keeping our feet firmly on the ground. Yet, to a particle physicist, gravity is astonishingly, inexplicably feeble. This is the hierarchy problem, a fundamental crack in our model of the universe where one of nature's four fundamental forces refuses to play by the same rules as the others. The electromagnetic force, which binds atoms, is about 10 to the 36 times stronger than gravity. To grasp this absurd difference, imagine the entire energy output of the sun compared to the faint warmth of a single candle flame. Why is there such a staggering imbalance? Our best theory, the standard model of particle physics, expects a certain elegance and uniformity, but gravity is a blatant outlier, a cosmic rule break on an epic scale. The problem becomes even sharper when we consider the Higgs boson, the particle that gives all others mass. For the Higgs to have the relatively light mass that we observe, a miraculous cancellation must occur, balancing enormous numbers to an almost impossible degree of precision. It is as if you had to subtract two numbers, each a billion miles long, and end up with exactly 5. Without this unnatural fine-tuning, the Higgs should have a mass so colossal that it would have collapsed the universe in on itself moments after the Big Bang. This delicate balance suggests that our current understanding is incomplete, that something is missing from the equations. Physicists like Nima Arkani have proposed radical solutions that rewrite our concept of reality itself. One compelling idea is that gravity only appears weak because it is not confined to our three-dimensional world like the other forces. It could be leaking into extra, hidden spatial dimensions that are curled up so tiny we cannot perceive them. Think of our universe as a vast, three-dimensional sheet of paper. The strong and electromagnetic forces are drawn in ink, trapped on the paper's surface. But gravity is like a whisper that can travel through the very bulk of the room, its strength dissipating into these unseen dimensions. This would explain why it feels so diluted in our experience. Another leading theory, supersymmetry, proposes that every known particle has a hidden, heavier superpartner. These shadow particles would naturally cancel out the extreme quantum effects that make the Higgs mass so unstable, solving the hierarchy problem with elegant symmetry. For decades, physicists hoped the Large Hadron Collider would discover these superpartners, providing a beautiful resolution. Yet, after years of smashing protons together at unprecedented energies, no evidence for supersymmetry has emerged. The detectors remain silent, deepening the mystery rather than solving it. The hierarchy problem stands as a stark reminder that the universe's rulebook might be written in a language we have not yet learned, a language that could include curled-up dimensions or particles existing in a shadow realm just beyond our current perception. If the fundamental forces cannot even agree on a common strength, what other basic assumptions about reality are waiting to be overturned? Even the faintest whisper from the birth of the universe can shatter our most cherished assumptions. The cosmic microwave background is that whisper, a nearly uniform glow of radiation that fills the entire sky, a remnant from when the cosmos was just 380,000 years old. For decades, this afterglow of the Big Bang has been our strongest evidence for a fundamental rule called the cosmological principle. This principle states that the universe, on the largest scales, is isotropic and homogeneous. In simpler terms, it should look the same in every direction, with no special places and no preferred axis. It is the foundation of modern cosmology, the reason we can assume that the laws of physics are the same everywhere. But then, we mapped it in exquisite detail with satellites like Planck, and we found something deeply unsettling. The fluctuations in the background radiation, the tiny temperature variations that seeded all the galaxies and voids we see today, are not completely random. They appear to be aligned along a particular axis, a mysterious direction in space that some cosmologists have dramatically nicknamed the axis of evil. This is not a small statistical fluke, it is a glaring anomaly that seems to point a finger across the cosmos, suggesting a preferred direction, a cosmic north if you will. The name itself, coined by researcher Joe Megiddo, reflects the profound threat this alignment poses to our standard model. If the universe has a preferred axis, then the cosmological principle is broken. We are not living in a random, featureless cosmos, but in one that may have a hidden structure, a fundamental lopsidedness written into its very first light. Researchers like Kate Land have described it as the most significant anomaly in the CMB, something that simply should not be there if our basic assumptions are correct. What could possibly cause such an alignment? Perhaps it is a ghostly imprint from a time before the Big Bang, a drag from a neighboring universe in a vast multiverse. Or maybe it is evidence that the fabric of space-time itself is anisotropic, stretching differently in one direction than in others. The very idea forces us to question whether we are at the center of some grand cosmic asymmetry, or if what we see is just a local flaw in an otherwise uniform reality. If the universe has a secret axis, what other hidden geometries are woven into the fabric of space, waiting to tilt our understanding of reality once more? Even the most ghostly particles in the universe hold secrets that can overturn entire theories. Neutrinos are the phantoms of the particle world, streaming through you in their trillions every second, barely interacting with matter. For decades, the standard model of particle physics, our most complete catalog of the subatomic realm, classified them as massless travelers moving at the speed of light. They were assumed to be ethereal spectators obeying a simple and elegant rule, but the universe had a surprise in store. Deep underground, in colossal tanks of ultra-pure water like Japan's Super Kamiok, an experiment, scientists began to notice something strange. They were detecting neutrinos produced by cosmic rays in the atmosphere above, but the number arriving from directly through the Earth did not match the number coming from the atmosphere on the other side of the planet. It was as if some of the neutrinos were disappearing during their journey. They were not vanishing, they were transforming. A neutrino born as one type, say an electron neutrino, could spontaneously change into a muon or tau neutrino as it traveled. This phenomenon, called neutrino oscillation, was a bombshell. The physicist Takaaki Kajita, who shared the Nobel Prize for this discovery, described it as clear evidence that our understanding of neutrinos was fundamentally flawed. The chameleon-like change is only possible if neutrinos have mass, however tiny. A massless particle, like a photon of light, experiences no time and cannot change its identity. But a particle with mass travels at less than the speed of light, and for it, time passes, allowing this incredible metamorphosis to occur. This was a direct violation of the Standard Model's original rulebook. Think of a chameleon that you observe to be green. You look away for a moment, and when you look back, it is red. You assume it must have changed color deliberately. But then you discover it actually transforms based on the distance it travels, not the color of its surroundings, revealing a hidden property you never knew it possessed. The discovery of neutrino mass forced physicists to acknowledge a glaring hole in their most successful theory. It is a clear sign that the Standard Model, for all its predictive power, is not the final word. This tiny, almost imperceptible mass points toward physics beyond the model, perhaps to a grander, more symmetric theory that can incorporate these ghostly particles properly. If something as fundamental as the mass of a neutrino was hidden in plain sight, what other basic properties of reality have we gotten completely wrong? This subtle shift in our understanding of the smallest things leads to a cosmic scale paradox, where the universe itself seems to be missing its most basic ingredients. Our cosmic inventory holds a stubborn error that refuses to be corrected. When the universe was just minutes old, a frenzied burst of nuclear fusion forged the first simple elements, a process we call Big Bang nucleosynthesis. The calculations for this primordial cookbook are remarkably precise, predicting the amounts of hydrogen and helium we see across the cosmos with stunning accuracy. Yet for one element, the math is catastrophically wrong. The models predict that a certain isotope, lithium-7, should be about 3 times more abundant in the oldest stars than what we actually observe. This is the lithium problem, a small number with massive implications, suggesting our understanding of the universe's first moments is fundamentally flawed. For decades, cosmologists have wrestled with this discrepancy. Could unknown nuclear reaction rates be to blame? Or does the answer lie in the stars themselves, with ancient stellar processes somehow destroying the lithium over billions of years? The most thrilling possibility is that the error points to entirely new physics. Perhaps an unknown particle, like a lightweight cousin of the neutron, was present in the early furnace, subtly altering the nuclear chain reaction and consuming the extra lithium. This would mean our entire timeline of cosmic creation is missing a key character. We are like detectives who have perfectly reconstructed a crime scene, only to find one piece of evidence that points to an intruder no one saw. The lithium problem is a quiet but persistent alarm bell, reminding us that the rulebook for the universe's birth may contain chapters we have not yet read. If we cannot even account for the creation of a single, simple element, what other secrets are hidden within the recipe for reality itself? This elemental mystery connects to a far more dramatic breakdown, one that unfolds not in the past, but in the violent present of the cosmos's most powerful explosions. Einstein's theory of relativity gave us one of the most profound and poetic rules of the cosmos. Gravity is the curvature of space-time, and a massive object doesn't just warp space, it warps time itself. Near a planet or a star, time slows down. This is not a metaphor, it is a measurable physical reality. An atomic clock placed at sea level will tick slightly slower than an identical clock on a mountaintop, farther from Earth's gravitational pull. The difference is minuscule, but it is real. We rely on this precise effect every single day. the Global Positioning System, a network of satellites orbiting high above the Earth, must account for this time warp. Because the satellites are in a weaker gravitational field and moving at high speed, their onboard clocks run faster than clocks on the ground. If engineers did not correct for this relativistic drift, GPS coordinates would be off by several miles within just a few hours, rendering the system useless. This is a triumph of Einstein's theory, a rule applied with spectacular success. Yet, even here, in this well-tested domain, there are whispers of a deviation. When measurements are taken with excruciating precision, the time dilation experienced by these satellites does not always match predictions with perfect accuracy. The discrepancies are tiny, almost vanishingly so, but they are persistent. It is as if every clock in the world agreed to tell time almost perfectly, except for a handful that consistently gain or lose a fraction of a second for no apparent reason. What could be causing this subtle mismatch? Some physicists point to phenomena like gravitomagnetism, an effect predicted by general relativity where a rotating massive body, like the Earth, drags the fabric of space-time around with it, creating a kind of gravitational whirlpool. This frame dragging could impart an additional, almost imperceptible twist to time itself. Others wonder if this is a hint that our understanding of gravity is incomplete on certain scales, leading to theories of modified gravity that subtly alter Einstein's equations. Experiments have placed atomic clocks in laboratories at different heights, confirming the basic time dilation effect with astounding accuracy. But the quest continues to measure it with even greater precision, to see if the universe's timekeeping holds a secret clause we have yet to read. This tells us that even our most well-established rules might operate with hidden exceptions. If time, the most fundamental rhythm of reality, can tick with a slight but mysterious irregularity, what other cosmic constants might be quietly, subtly, breaking their own rules without warning? Even the atoms that build our world, the familiar stuff of stars and planets, are part of a cosmic case of missing matter. We can calculate with great precision how much ordinary matter, or baryonic matter, should have been created in the Big Bang. This includes the protons and neutrons that make up everything we can see. Yet, when astronomers add up all the visible stars, galaxies, and gas clouds in the nearby universe, the total falls shockingly short. Nearly half of all the ordinary matter that should be there is simply gone. It is as if you carefully counted every ingredient for a massive recipe, only to discover that half the flour has vanished from your kitchen before you even started baking. This is not dark matter, which is a separate and even larger mystery. This is the stuff we are made of, and it has seemingly disappeared without a trace, breaking one of the most fundamental rules of all, the conservation of matter and energy. The universe cannot simply lose half of its atoms. They must be hiding somewhere. The leading theory suggests this missing matter is not in bright, dense clumps but spread throughout the vast, empty spaces between galaxies in a diffuse cosmic web. Imagine a ghostly, superheated fog, a plasma so tenuous and hot that it is completely invisible to our telescopes. Astronomers hunt for this warm, hot, intergalactic medium by using the brightest objects in the universe as backlights. When the light from a distant quasar travels billions of light years to reach us, it passes through these invisible filaments. Specific wavelengths of light are absorbed, creating a unique fingerprint in the quasar's spectrum that betrays the presence of the otherwise hidden gas. It is detective work on a galactic scale, finding the culprit by the shadow it casts. Finding this missing matter is crucial because without it, our models of how galaxies form and evolve are incomplete. How can we understand the architecture of the cosmos if we cannot even account for the bricks? This search forces us to confront a humbling truth, that the universe may be filled with entire structures and reservoirs of ordinary material that are simply too faint, too diffuse or too hot for our current instruments to see directly. If we are missing half of the normal stuff, what other forms of matter and energy, entirely unknown to us, are woven into the fabric of the void? The search for our missing atoms reveals a cosmos more complex than we imagined, but the very tools we use to measure it are now betraying us. The Hubble constant, the number that tells us how fast the universe is expanding, has become a source of profound disagreement. For years, we assumed this fundamental parameter was a single, reliable figure, a cosmic speed limit we could pin down with ever-increasing precision. Instead, we have found ourselves in the middle of a crisis known as the Hubble Tension. It begins with two different ways of measuring the expansion. One method looks into the deep past using the cosmic microwave background, the afterglow of the Big Bang. By analyzing the subtle patterns in this ancient light with satellites like Planck, scientists can extrapolate the universe's expansion history and calculate what the Hubble constant should be today. This is a measurement from the beginning of time. The other method looks at the present-day universe. Astronomers like Nobel laureate Adam Rees use cosmic lighthouses, such as Cepheid variable stars and certain types of supernova in nearby galaxies. These objects have a known intrinsic brightness, so by measuring how dim they appear, we can gauge their distance and, in turn, the current expansion rate. These are our local cosmic rulers. The problem is stark. The two methods do not agree. The present-day universe appears to be expanding significantly faster than the extrapolation from the early universe predicts. It is as if you used two different tape measures to check the height of a doorframe, and one consistently gave you a result several inches taller than the other. As Adam Rees has stated, this is not just a small statistical fluke. It is a growing discrepancy that has persisted despite more precise measurements. The tension suggests a fundamental flaw in our understanding. Perhaps dark energy, the force driving cosmic acceleration, is not constant but has evolved over time, becoming stronger than our models allow. Or maybe there are extra, unknown types of neutrinos or other exotic particles that flooded the early universe, subtly altering its expansion history. The most exciting possibility is that this discrepancy is a direct signal of new physics, a crack in the cosmological model that forces us to revise our most basic assumptions about the cosmos. If our cosmic rulers cannot agree, then the very fabric of space-time might be governed by rules we have not yet discovered. This measurement crisis sets the stage for a far more violent and energetic breakdown, one that erupts from the depths of space with unimaginable power. A particle approaches an impenetrable wall. According to every classical law of physics, it simply does not have the energy to climb over it. It should bounce back every single time. But in the quantum realm, rules are written in smoke. There is a chance, however small, that the particle will not bounce back at all. Instead, it will vanish from one side of the wall and instantly reappear on the other, as if it had simply tunneled through the impossible barrier. This is not science fiction, this is quantum tunneling, and it is a fundamental rule break that powers the universe itself. Inside the heart of every star, including our own sun, protons are constantly trying to fuse together to create helium and release the energy that makes stars shine. But there is a problem. Each proton carries a positive electric charge, and positive charges repel each other with tremendous force. To overcome this repulsion and get close enough to fuse, the protons would need to be moving at speeds achievable only at temperatures far higher than those found in the sun's core. Classically, the sun should not shine. It is quantum tunneling that provides the miraculous loophole. There is a tiny but non-zero probability that a proton can tunnel through the immense energy barrier of electrical repulsion, allowing fusion to occur and bathing our solar system in life-giving light. Without this quantum cheat code, the universe would be dark and lifeless. This same process is at work in radioactive decay, where an alpha particle, 2 protons and 2 neutrons bound together, tunnels out of the nucleus of a heavy atom like uranium. The particle is trapped inside a nuclear prison by a powerful energy barrier, yet it spontaneously escapes, breaking a rule that seems absolute. As the physicist George Gamow described it, the particle does not jump over the wall, it literally digs a tunnel through it. This defiance is not just a cosmic curiosity, it is the bedrock of modern technology. The tunnel diode, a semiconductor device, relies entirely on quantum tunneling to allow electrons to pass through an insulating layer, enabling incredibly fast switching speeds that are vital for high-frequency applications. Think of it this way, it is as if you were standing in a room with no doors or windows, and you decided to simply walk through the wall. To everyone else in the room, you would have vanished from one side and materialized on the other, defying all logic. In the quantum world, this is not magic, it is probability. The particle does not physically bore a hole, it simply has a wave-like nature, and that wave extends, however faintly, into the barrier and beyond. There is a chance, a statistical likelihood, that the particle will be found on the other side. This reveals a universe where impossibility is merely a matter of odds, and where the seemingly solid walls of reality are, at their core, permeable. If particles can tunnel through barriers, what other impossibilities are just waiting for the right roll of the cosmic dice, leading us to a place where the very concept of a vacuum is not empty at all, but seething with untold energy. The universe's expansion rate is not the only cosmic parameter that seems unnaturally perfect. Geometry itself holds a profound mystery. According to Einstein's theory, the fabric of spacetime can be curved by the matter and energy within it. This leads to 3 possible fates for the cosmos: a universe with positive curvature that eventually collapses in a big crunch, one with negative curvature that expands forever into a thin, cold void, or a universe that is perfectly flat, balanced on a razor's edge. Every measurement we have ever made, from the cosmic microwave background to the large-scale distribution of galaxies, points unequivocally to a flat universe. The problem is that this flatness is incredibly fragile. For the universe to remain flat after nearly 14 billion years of expansion, its initial conditions had to be fine-tuned to an astonishing degree of precision. At 1 second after the Big Bang, the density of the universe had to be balanced to within 1 part in 10 to the 15th power. That is a precision equivalent to balancing a pencil perfectly on its tip, not for a moment but for billions of years. Such a perfect setup defies all odds, breaking the expectation that the early universe should have been chaotic and uneven. It is as if the cosmos was born with a specific, perfect geometry programmed into its very foundation. Cosmologist Roger Penrose has long questioned this apparent fine-tuning, arguing that the initial low entropy state needed for such flatness is even more unlikely than the current state of the universe. He proposes alternative explanations such as conformal cyclic cosmology, where the universe goes through endless cycles, and the apparent fine-tuning is a result of the transition from one eon to the next. The leading solution, cosmic inflation, suggests that a brief period of hyper-expansion stretched the universe so dramatically that any initial curvature was smoothed out into the flatness we observe today. Think of blowing up a wrinkled balloon to the size of a planet. The surface would appear flat to anyone standing on it, yet this only pushes the mystery back a step. Why did inflation start, and what physical law dictated that it would end with such perfect balance? The flatness problem forces us to confront the unsettling possibility that our universe is not just a random occurrence, but one that was set up with inexplicable precision. Was this a cosmic accident of unimaginable luck, or is there a deeper principle at work, a rule we have not yet uncovered, that naturally leads to such perfect geometric balance? This question of a universe seemingly designed for stability leads us to an even stranger idea, where the reality we experience might not be the primary one at all. Mirrors should reflect a perfect, reversed image of reality, but what if they did not? This is the heart of a deep puzzle in the subatomic world known as the strong CP problem. It involves two fundamental symmetries, charge conjugation, which swaps a particle with its antimatter counterpart, and parity, which creates a mirror image. For most forces in nature, it is perfectly acceptable to break this combined CP symmetry. The weak nuclear force responsible for radioactive decay does it all the time, which is why our universe is made of matter and not antimatter. But the strong nuclear force, the incredibly powerful glue that holds the nuclei of atoms together, appears to follow a different set of rules. Our most successful theory of this force, quantum chromodynamics, naturally allows for a violation of CP symmetry. It should be possible for the force to distinguish between a particle and its mirror-reflected antimatter version. This would have a visible consequence. It would give the neutron a tiny, measurable electric dipole moment, a slight separation of positive and negative charge. Yet, when physicists search for this effect with exquisitely sensitive experiments, they find nothing. The neutron is electrically neutral to an astonishing degree of perfection. It is as if you held up a perfectly strange object to a mirror, and instead of seeing its reflection reversed, you saw an identical, unreversed copy. This is not just a minor detail, it is a profound mystery. Why does the strong force, alone among the fundamental forces, refuse to break a symmetry that the equations say it should be allowed to break? This unnatural perfection suggests that a crucial piece of physics is missing from our equations. To resolve this, physicist Frank Wilczek proposed an elegant solution, a new particle called the axion. The axion would act as a kind of cosmic corrective field, subtly interacting with the strong force to cancel out any possible CP violation, forcing the neutron to remain perfectly neutral. Think of it as a hidden thermostat that automatically adjusts to maintain a perfect balance, preventing the universe from tilting in a way the rules say it could. This is not just a theoretical fix. Axions are now a leading candidate for dark matter. These ghostly particles streaming through space in vast numbers could be the invisible mass holding galaxies together. Experiments are underway to detect them, using powerful magnets and ultra-sensitive detectors in a hunt for these elusive rule breakers. The strong CP problem is a quiet but glaring exception, a law of physics that the universe seems to have chosen not to enforce, pointing toward a shadow world of particles and forces that could redefine reality. If the strongest force in nature obeys a symmetry it should be allowed to ignore, what other hidden principles are secretly governing the cosmos, perhaps even determining the ultimate fate of everything we see? The most precise measurements can reveal the deepest cracks. For decades, the standard model of particle physics has predicted the magnetic personality of every fundamental particle with breathtaking accuracy. But one particle, the heavier, unstable cousin of the electron known as the muon, refuses to follow the script. Its magnetic moment, a measure of how it wobbles like a tiny top when placed in a magnetic field, is ever so slightly off. This is not a failure of the theory, it is a whisper from the unknown. At experiments like the one at Fermilab called G-2, scientists create beams of muons and send them racing around a giant, superconducting magnetic ring. They measure the muon's wobble with a precision equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. And the result is a persistent anomaly. The muon wobbles a fraction more than the standard model says it should. As scientist Brendan Casey noted, this anomaly has now reached a significance of 5 sigma, a threshold in particle physics that officially qualifies as a discovery, not a fluke. It is a rule break that cannot be ignored. What could be causing this extra wobble? The leading, thrilling possibility is that the muon is feeling the influence of particles or forces that are not part of our current model. Imagine you are dancing alone in a room following a specific rhythm, but if unseen dancers are also in the room, their movements would subtly tug on you, altering your dance in a way that betrays their presence. The muon's anomalous magnetic moment suggests it is dancing with invisible partners. These could be supersymmetric particles, or perhaps something even more exotic, like a new fundamental force that interacts only very weakly with ordinary matter. This tiny deviation is a beacon pointing toward a vast, hidden sector of reality. It tells us that our catalog of the universe's ingredients is profoundly incomplete. If the wobble of a single, fleeting particle can hint at an entire zoo of undiscovered physics, what other fundamental properties have we measured incorrectly, waiting for the right experiment to reveal their true, rule-breaking nature? Our most precise theories have led to the worst prediction in the history of science. Quantum field theory tells us that the vacuum of space is not truly empty. It is a seething, bubbling sea of virtual particles, constantly flickering in and out of existence. Every cubic centimeter of nothingness should be filled with a colossal amount of energy, a fundamental background hum from these quantum fluctuations. When we calculate this vacuum energy density, the number is so unimaginably huge it defies comprehension. It should be around 1 followed by 120 zeros. This energy would act as a repulsive force, a cosmological constant, so powerful that it would have ripped the infant universe apart in a fraction of a second. Stars and galaxies could never have formed. Yet, when we measure the actual expansion of the cosmos driven by dark energy, the observed value of this cosmological constant is almost zero. Not just a little smaller, but 1 followed by 120 zeros times smaller. The discrepancy is so vast it is like predicting an ocean should have the mass of the entire observable universe, but when you dip a cup into it, you find only a single drop of water. The physicist Steven Weinberg called this the worst theoretical prediction in the history of physics. It is not a small error, it is a catastrophic failure that reveals a fundamental gap in our understanding. How can the theoretical and observed values of nothing be so spectacularly different? The vacuum catastrophe suggests that our concept of empty space is profoundly wrong. Perhaps some unknown symmetry cancels out the enormous quantum energy with near-perfect precision, a cancellation so fine-tuned it seems miraculous. Or maybe the vacuum energy is not constant, but dynamic, evolving over the lifetime of the cosmos to its current, strangely quiet state. This immense gap between calculation and observation is a screaming alarm that the rules of quantum mechanics and general relativity are fundamentally incompatible when they meet in the void. Empty space is not a passive stage, but an active participant in the cosmos, holding a secret about its own energy that we are only beginning to glimpse. If the void itself can break the rules so dramatically, what other impossibilities are woven into the fabric of nothingness, waiting to reveal themselves in the most energetic events imaginable? Even the ultimate cosmic pressure cookers, neutron stars, are starting to leak. According to general relativity, there is a strict upper limit to how massive a collapsed star can be before gravity wins completely, crushing it into a black hole. This Tolman-Oppenheimer-Volkoff limit was thought to be an unbreakable rule, a final boundary between a super-dense star and an absolute singularity. But the universe, it seems, has other plans. Observations of massive pulsars, like the one known as PSRJ 0348 plus 0432, reveal neutron stars that appear to be pushing against this theoretical ceiling. With masses estimated at over 2 times that of our Sun packed into a sphere the size of a city, these objects are so dense that a single teaspoon of their material would weigh billions of tons. The pressure at their cores is unimaginable, squeezing matter into states we cannot recreate in any laboratory. The existence of such heavy neutron stars suggests that the equations of state, the rules governing how matter behaves under such extreme conditions, might be wrong. It is like blowing up a balloon knowing it should pop at a certain pressure, only to watch it keep expanding, its rubber stretching in ways you thought were impossible. As astrophysicist Thankful Cromarty has noted, these massive pulsars are cosmic laboratories, testing the laws of physics in regimes we can only observe from afar. The recent detection of gravitational waves from neutron star mergers by observatories like LIGO and Virgo adds another layer of mystery. The signals from these violent collisions hint that the resulting object might have briefly existed as a supermassive neutron star before collapsing, surviving for a few precious milliseconds longer than our models allow. This defiance of the mass limit forces a profound question. Are neutron stars made of something stranger than we thought? Perhaps their cores contain exotic particles like hyperons or deconfined quarks, creating a pressure that counteracts gravity more effectively than standard neutron-degenerate matter. Or maybe our understanding of gravity itself needs revision at these incredible densities. Each massive neutron star we discover is a crack in the rulebook of stellar evolution, challenging the finality of the black hole's birth. If a star can cheat gravity's ultimate victory, even for a moment, then the line between star and singularity becomes blurred, leading us to a place where the very nature of matter is not just unknown, but perhaps unknowable. Even the simple act of motion can rewrite the rules of reality. For an observer drifting through the vacuum of space, the universe is quiet and empty. But for an observer who begins to accelerate, the vacuum suddenly comes alive. This is the Unruh Effect, a quantum phenomenon so strange it suggests that the very existence of particles depends on your state of motion. As physicist Bill Unruh, who first described this effect, has noted, it forces us to accept that the particle content of the universe is not an absolute truth, but a relative experience. Imagine standing perfectly still on a calm day, feeling no wind at all. Now imagine starting to run. Suddenly, you feel a rush of air against your face. The Unruh Effect is analogous, but for the fabric of space itself. An accelerating observer does not just feel a fictional force, they perceive a warm bath of real particles popping into existence around them, particles that are completely undetectable to an observer moving at a constant velocity. This directly breaks one of our most fundamental assumptions, that the vacuum is the same for everyone. The implications are deeply entwined with Hawking radiation. Just as acceleration through empty space creates particles, the immense gravitational acceleration at the edge of a black hole does the same, producing the radiation that slowly evaporates it. This connection reveals a profound link between acceleration, gravity, and thermodynamics, suggesting that temperature itself is not an intrinsic property, but a consequence of motion through space-time. What does this mean for the nature of reality? If particles can appear or disappear based solely on how we move, then our entire inventory of the cosmos becomes a matter of perspective. It forces us to ask whether the universe is made of things, or if things are merely excitations we perceive when we interact with the void in a certain way. This relativity of existence hints that the observer is not separate from the system, but an active participant in its creation. When even the definition of nothing depends on your journey, the next cosmic anomaly reveals a flaw in our most basic map of the universe. The equations that aim to unite quantum mechanics and general relativity erase time from the universe. At the heart of this profound puzzle sits the Wheeler-DeWitt Equation, a mathematical framework for quantum gravity that simply does not contain the variable for time. It describes a cosmos frozen in a single, eternal moment, a stark contradiction to our most basic experience of past, present, and future flowing relentlessly forward. This is not a minor oversight, it is a fundamental feature of the theory, suggesting that time as we know it might be an illusion, an emergent property that arises from a more fundamental, timeless reality. It is like looking at the most sophisticated clock ever built, one that tracks every conceivable cosmic variable, only to realize it has no hands. The physicist Carlo Rovelli has spent decades grappling with this timelessness, suggesting that our perception of time's flow is a result of our limited thermodynamic perspective, a consequence of the universe's increasing disorder rather than a fundamental feature of the cosmos. The Wheeler-DeWitt Equation presents a universe where everything that ever was or will be exists simultaneously in a vast static block. This challenges the very goal of unifying our two great theories, for how can we merge a quantum world of change and probability with a relativistic description of dynamic spacetime if time itself vanishes from the final equation? The implications ripple from the theoretical to the deeply personal. If time is not fundamental, what does that mean for free will, for memory, for the progression of cause and effect? Are we just complex patterns in an eternal, unchanging tapestry, merely imagining our journey from birth to death? This mathematical rule break forces us to consider that the river of time we navigate every day might be a shallow stream atop a bedrock of timelessness, a powerful illusion crafted by the universe to hide its most Chinese letter secret. Even Einstein was deeply unsettled by the implications of this ghostly connection. His famous phrase, "spooky action at a distance," was not an endorsement but a complaint, a declaration that the universe simply could not operate in such a bizarre manner. He, along with colleagues Boris Podolsky and Nathan Rosen, formulated the EPR paradox as a thought experiment meant to highlight the absurdity of quantum mechanics. They argued that if quantum theory were correct, it would mean that measuring one particle could instantly influence another, regardless of the distance separating them. This, to Einstein, violated the core principle of locality, the idea that objects are only directly influenced by their immediate surroundings, and that no information can travel faster than light. For him, the universe was local and realistic, meaning objects have definite properties even when we are not looking at them, and influences cannot propagate instantaneously. The EPR paradox was intended to show that quantum mechanics was either incomplete or just plain wrong. Decades later, however, technology advanced to the point where this philosophical debate could be settled by experiment. Physicist John Stuart Bell devised a mathematical theorem that provided a clear test. He showed that if hidden variables, secret instructions carried by the particles that predetermine their states, were responsible for the correlation, then the results of certain measurements would fall within a specific range. But if quantum mechanics was correct and the connection was truly non-local, the results would fall outside that range. When these experiments were finally conducted, most notably by Alain Aspect and his team in the 1980s, the results were unambiguous. The quantum particles defied the limits of local realism. Their correlation was stronger than any hidden variable theory could possibly allow. It was a direct confirmation of the very spookiness that Einstein had rejected. Imagine two dice, one on Earth and one on a planet orbiting a distant star. You roll the die on Earth and it comes up a 6. Instantly, and without fail, the die light years away also shows a 6. This is not because a signal traveled between them, but because their fates were intertwined from the moment they were created. This is the essence of non-locality, a rule break that suggests the universe is fundamentally interconnected in a way that makes a mockery of distance. What does it mean for our understanding of reality if separateness is an illusion? If two particles can be parts of a single whole, instantaneously coordinating their behavior across the cosmos, then are we, and everything we see, also part of a deeper, unified fabric that transcends the space between us. This profound interconnectedness forces us to confront the final, and perhaps most startling, way the universe breaks its own rules. This final and perhaps most mind-bending violation suggests that the three-dimensional reality we experience is a grand illusion, a hologram projected from a two-dimensional surface at the edge of the cosmos. The seeds for this radical idea, the holographic principle, were sown in the fiery paradox of black holes. Remember the crisis of information seemingly vanishing into a singularity. Physicists like Gerard T. Hooft and Leonard Susskind realized that if information cannot be destroyed, then all the data describing everything that falls into a black hole must be encoded and preserved on its event horizon, the two-dimensional boundary surface. The three-dimensional interior of the black hole, with its crushing singularity, would then be a projection of that information. Susskind described this as a profound shift, implying that the world is in some sense a hologram. Think of the security hologram on your credit card. It appears to have depth and solidity, a full three-dimensional image, yet all of its information is stored on a flat, two-dimensional surface. The universe might operate on the same principle. The stars, planets, and the very space between them could be a magnificent projection from a vast, complex cosmic film located at the boundary of the observable universe. This principle shatters our most basic rule about dimensions. We assume we live in a world with three spatial dimensions, but the holographic principle suggests that this is an emergent property, not a fundamental one. The true, fundamental description of reality might require one less dimension, with our perception of depth being a consequence of how the information on that boundary surface is processed. This is not just a wild speculation. In string theory, certain calculations that are impossibly difficult in a three-dimensional space become tractable when translated into a two-dimensional framework, providing a powerful mathematical hint that this duality might be real. If the holographic principle is correct, it would be the ultimate cosmic rule break, revealing that the universe is not what it seems. Every particle, every force, and even the passage of time itself could be pixels in a cosmic projection, a simulation running on a distant screen we can never see. This single, unifying idea could resolve many of the paradoxes we have encountered, from the nature of information in black holes to the vanishing of time in quantum gravity. It suggests that the 22 ways the universe breaks its own rules are not random failures, but clues pointing toward a reality far stranger and more interconnected than we ever dared to believe. From the ghostly influence of dark matter to the holographic projection of reality itself, each of these 22 cosmic anomalies serves as a profound reminder that our understanding is a fragile and evolving construct. We have built magnificent cathedrals of theory only to watch the universe quietly point out the cracks in their foundations. These are not failures of science, but its greatest triumphs, signposts marking the frontier of human knowledge. They humble us, revealing that for every question we answer, a dozen more, deeper and more bewildering, rise to take its place. Science, then, is not a destination where all is known, but a perpetual journey of discovery. The physicist Carl Sagan captured this spirit perfectly when he said, "Somewhere, something incredible is waiting to be known." This is the true message of the cosmos, an invitation to remain curious, to keep questioning, and to embrace the beautiful, unsettling mystery of it all. Which of these rule-breaking phenomena captivates you the most? Share your thoughts in the comments, and if this journey through cosmic contradictions has sparked your wonder, subscribe for more explorations into the deepest secrets of space and time. The universe has shown us it is far stranger than we can suppose, and the next great revelation is always just beyond the horizon, waiting.